Good morning. Hello, everyone. Hello, hello. Good morning, good afternoon, good evening, depending upon where you're at in the world. Thank you so much for being with us here today. We really appreciate this opportunity to bring this exciting topic with you today. So speaking of the topic, what are we going to be talking about? Well, we're going to be talking about the characterization of the microstructure of electronic and semiconductor materials. But before we jump in, I do want to point out that on your screen there, you should see a chat function, a chat bubble. Please don't hesitate to, as we're going along, to submit questions that you have. We will have a Q&A at the end, but as we're going along, if something pops up, please don't hesitate, as I said, to go ahead and put those in there. Okay, let's go ahead and jump right in. I'm going to run through the speakers here. Let's do a quick introduction of everyone. If you didn't notice already, that's me there on the left. Hello, everyone. My name is Steven Hernandez. I'm a business development manager here with Carl Zeiss Microscopy in North America. I cover many different industries, including the industrial raw materials sector. I have over 15 years of experience in electron microscopy, as well as general microscopy from academic core facilities where I was a research specialist, high volume manufacturing with Intel, as well as failure analysis on medical devices with Medtronic. Also with us here today is 𝗠cie𝗿𝗄𝘀. Andy has 20 years experience in chemicals, catalysts, metals, renewables, and microanalysis. After graduating as a Master of Chemistry from York, he has worked in the automotive, metals, fuels, jewelry, and materials sectors, including 10 years with Johnson Matthey. He is now the global head of industrial materials sector at ZEISS Microscopy based in Cambridge, UK. Last but definitely not least, Dr. Rhea Mitchell is a skilled researcher and applications development engineer with a strong background in imaging technologies and sedimentology. She has held prestigious positions at institutions such as the Natural History Museum and 𝗠cie𝗿𝗄𝘀 University, where she developed innovative imaging techniques. Currently, she works at ZEISS Microscopy, focusing on raw material applications across various industries. So that's the lineup for you today. I myself am going to be taking a little bit more of a moderator role. I'll kick things off and then hand it over to Andy and Rhea, who will be taking us through this really engaging and intriguing, insightful topic, something that they've been working together on recently. So here's a quick little idea of the general layout of today. Like I said, I'll kick things off and talking about, well, who is Carl Zeiss? Who is Carl? And what do we do? It's always nice to be able to have this opportunity to talk about us. And it leads really nicely, actually, into talking to Andy's sections here as we talk about the role of microscopy and the uniqueness of ZEISS solutions. And then Rhea's going to bring us home and really dig into those advanced applications for semiconductor and electronic materials. Okay, so who's ZEISS? Well, we've been innovating in microscopy for almost 200 years now. So we're a global company. We're headquartered in Oberkochen, Germany. We have up to 100 locations worldwide in 50 different countries. And you might be thinking, Steven, that's a lot of microscopes in a lot of different places. Well, as any global company, we have multiple divisions, including our semiconductor manufacturing technologies, our industrial quality and research solutions, our medical technologies, and even our consumer markets. So these advanced technologies all the way from optics for these ASML EUV systems, advanced microscopy solutions, advanced microsurgery solutions, but even the consumer's market. So scopes, rangefinders, camera lenses. Many of you actually might be consumers of those products, but that's how we're divided up as a company throughout the world. And not to spend too much more time into it, but just to give you a better idea about who you're speaking with today, these individual divisions are broken up further. And today, Andy, Rhea, and myself are part of this research microscopy solutions, which is the subunit here of the industrial quality research sector, or business unit. Also, what is, again, not just a global presence, but what does 200 years of innovating in microscopy get you? Well, it gets you the broadest portfolio in microscopy, from light, X-ray, electron, and ion microscopy. We really truly cover the full multi-scale characterization spectrum here. So spatial resolutions all the way from centimeters, large samples, large fields of view, all the way down to nanometers, sub-nanometer resolution. But it's not just about resolution, right? we got to talk about what about the modality. That's why we have light. That's why we have X-ray electron, because it depends upon what information we're trying to get out of our material. It's not just about seeing small things. It might be about seeing specific types of materials. So this is where all these different innovations came from. And then what I like to say, and I'll spare my hammer and nail analogy, but there's a lot of hammers and there's a lot of nails out there that these systems have been developed for. So in RMS, that's who we are. That's our main focus. And speaking of those hammers and nails, I will hand it over to Andy now, and he's going to take us through where these hammers, these microscopes being used in the semiconductor electronic materials innovation, the uniqueness of these ZEISS solutions, and then we're going to dig into those advanced applications here. Okay, I'll hand it over to Andy.
Okay, fantastic. Stephen, can you hear me? Okay, cool. So welcome to this discussion about really the electronic raw materials that make the semiconductor and electronics industries and devices tick, the unique properties that the innovations that the individual materials must go through, and the novel materials that really make our modern connected world what it is, and that have and will change the world. So let's dig into what is materials microscopy to set the scene. Well, it's only really about four things, and please do correct me if you can think of any others. But really, when we look at our materials and devices, we're only really looking at a few different sets of parameters, their dimensions, their chemistry, how they interact with each other. So firstly, the grains, the structure, the grain and crystal structure, particularly of metallic devices, metallic materials, I should say, but also lots of other granular as well as amorphous materials. The particles, and that could be the active nanoparticles, it could be harmful inclusions or contamination particles, but so particles and inclusions. Whoops, time has gone wrong. And then the interfaces, and that includes surfaces. So the surfaces, interfaces, adhesions. So particularly in electronic devices, there are so many different interfaces and surfaces, all with adhesives and resins to bind them together, with electron transfer in batteries or heat transfer in heat sink and insulation materials. And that's one of the topics which Ria is going to talk about today. And then when we talked about all of those solid domain, you also, of course, have to talk about the pore domain and the voids and spaces within your materials. And the action of those, and they may be intended or they may be unwanted, such as porosity in ceramics or castings, that sort of thing. So really, grains and crystals, particles and inclusions, surfaces and interfaces, and the empty spaces too. And really, and materials innovations really are the key to the performance of those devices. So I've used the example of a mobile phone here, but every chip, every component, the packaging, all of that is underpinned by the advanced materials, and the way that that device works and any other device can be studied by microscopy in so many different ways. Firstly, the battery pack, and those of you who joined us for our battery materials webinar a few months ago may recognize our cathode and anode materials, of course. We've got a separator material here as well, next generation separator. We've got X-ray for non-destructive 3D scanning. We've got electron microscopy for high resolution nano imaging, and of course EDS as well, and our different analytical techniques. You might want to scan the camera module, and this is one that's been scanned non-destructively in the device using X-ray microscopy. Of course, we look at the semiconductor itself, the chips, the circuits, from the wafer to device, and the packaging and so on. And you might do that with focused ion beam, SEM. You might even want to look at the profilometry of the glass, so you can use confocal microscopy using laser light to look at the profile, any sort of scratches or texture within the glass. Adhesives and binder, and what you can see here is AI-based segmentation of binder on battery materials, so how they're actually bound within the device. And there's all sorts of materials that are sort of based on quite old-fashioned materials, films, polymers, and plastics, but they're all critical to the device performance. So films and membranes, of course, polymers, and here we've got polymer particle analysis based on segmentation, polyimide films, which are in so many of these devices. You might be looking at the solder in the control board. So this is from a non-destructive X-ray scan within the device. You could look at the foils and the other layers and the metallic foils. There's plenty of metallic foils in electronic devices. Here we've used diffraction contrast tomography to look at the grain structure non-destructively. Aluminum case, here we have some section of light microscopy and the coatings. So coatings and layers, here we are again talking about how they interact and interplay, and even in the case of coatings, change the color of that casing itself. There's a gyroscope in every mobile phone these days, of course, and this is a non-destructive X-ray scan. Graphene, material of the future, they could be in the touch-sensitive screen, they could be used as thermal insulation, and we have here a scanning electron microscopy image of that. Conductive gasket material, I know that Ria's going to go into some detail on this really interesting nano-engineered material, so conduction and insulation, both of heat and of current. And here we have an EDS analysis of a circuit board coating. So this is a copper strip board, actually. So we can see the copper layer and then the different particle basis below it. So you can see that there is a huge myriad number of advanced materials which really make these devices work. And although we're going to focus individually on the individual materials here, so we're going to look at how we characterize, how we develop and underpin all of that performance, which is really their materials problems. And so I've talked about X-ray microscopy. I know it's going to be a big part of Ria's talk, but I thought this sort of brings it to life. So here we have an iPhone. This has been scanned non-destructively at high resolution in one of our ZEISS X-ray microscopes. And you can see by this virtual fly through the material, you can see every layer at sub-nanometer 3D resolution. So you can see that those solder boards and that circuitry. You can see the induction loops. You can see here we have individual solder bumps in the processor. So here we're flying through the processor in cross section and looking at the structure of that. Zooming out again. We're about to zoom into the camera module. So you saw this image on the last slide. So in fact, you can see how these camera modules are actually really complex and not dissimilar to objectives in microscopes, in fact. But you can see they're an assembly of multiple lenses, but also materials and packaging. And of course, the battery as well, you can non-destructively image the battery itself. Here we go. So here we have the individual cathode, anode, and separator layers. And you can see the individual cathode grains, and you can even see some of the cracks and porosity non-destructively. So why this is useful, it's a great 3D image, but it's also very useful in endpointing and finding where to look when there's an issue or a problem with a battery, for example. Then X-ray microscopy tells you where to look the needle in the haystack. I also want to bring in, and I know Ria's going to touch on this as well, artificial intelligence. So we at ZEISS have been pioneers, I think, in the industrialization of AI in microscopy. And it can be put to work for lots of different jobs within the operation of the microscope for image acquisition, image processing, reconstruction, and segmentation in both 2D and 3D imaging. So from left to right, firstly, it's very, very good for denoising of data. So this is a FinFET fib stack of a FinFET device. So that data set, I hope you can see the, I'll go back through it, just that denoising step for that data set. So as we started a very noisy, pure raw image, denoising through AI is able to very much enhance the edges and reduce the noise and increase the signal to noise. We also use it for something called upscaling, and this is where you use a high-resolution small volume of a 3D data set and use the reconstruction of that to upscale a larger volume that's done in a faster scan or a lower resolution. So you can apply that reconstruction. So all 3D images are reconstructions, require reconstruction of their individual slices. So there are already algorithms involved in that process, and AI is able to reconstruct with lower noise, higher signal, and higher precision. And then we talk about segmentation. So segmentation is the extraction of information, actionable information from an image. Here we have a polymer image, and we've already used AI to pick out the individual particles of that polymer. Now that's really tricky in an electron micrograph, because you're looking literally at shades of grey. And when you've got particles which are overlapping or agglomerated, or where the image is not perfect, there may be some shadowing or charging, then actually it's very useful to be able to use AI to extrapolate exactly where that full particle is and the dimensions of it. So you won't be able to see everything underneath a 2D layer, but what you are able to do is do some much more precise particle analysis, even of overlapping particles. So here we have a instant segmentation, which means you're picking out individual objects. Much better than a normal grayscale thresholding approach could do. And finally, the fourth one is semantic segmentation. And what this means is you're doing phase analysis. So you're looking at, rather than looking at, you see 3 cats and 3 dogs in instant segmentation, in semantic segmentation, you're separating your image of cats versus dogs, if that makes sense. And that gives you a different form of data. So semantic segmentation will enable you to do phase classification. So in this case, this is a ceramic with pores and grain boundaries, 2 of our 4 disciplines. And here we've been able to analyze the grain boundaries and therefore the grain size, but also quantify the porosity in this particular ceramic sample. So instant segmentation is individual objects, semantic is phase classification and percentages. Quick word also on the role of microscopy, potential role of microscopy in the circular economy. So this is a technique called ZEISS phase identifier. We've got a 2D version and a 3D version for 2D datasets in SEM, and 3D datasets from X-ray microscopy. And we've been using these for analyzing composition and morphology of black mass. So this is battery scrap in the recycling industry. Here on the left with XRM, and on the right with field emission SEM, on our AI-based phase classification. And then we have here as well a mineralogical analysis of the components of electronic scrap. So 𝗍_waste, as it's called, and that's been done in an electron microscope using an EDS-based AI-powered mineralogy analysis. So I would just like to sum up this introduction with, really, as Stephen said, we've got a uniquely broad portfolio of microscopic techniques. And what we're doing here is characterizing our raw materials all across the length scales from millimeter to nanometer with multi-scale, multimodal, multi-physics techniques to power the materials revolution. So in X-ray microscopes, you get rapid, high volume, large, high resolution, large volume scanning and analytics with high resolution, but also high speed. Focused ion beam SEM, so that is our 𝗶_𝗶𝗹𝘀 for milling and studying things like interfaces and structures at the nanoscale. And we've also got a unique laser accessory available for that to do very fast milling and preparation of samples. Field emission SEM, so our flagship technology, really, with the superior low and very, very low kV, low power imaging of sensitive materials, which means you get a very, very good, crisp, clean image, even at very low accelerating voltage, which protects your sensitive materials. And so many of these are prone to beam damage with powerful multi-purpose analytics. We also have tungsten and Lab 6 conventional SEMs, thermionic SEMs, easy, flexible workhorses for your lab. And of course, the light microscopy with which it all started back in the 175 years ago with our renowned optics, modular hardware and automation. And then from that, image analysis and correlation with the rest of our portfolio. So I hope that gave you a flavor, really, of what we can do for the electronic raw materials industry. And at this point, I'm going to hand over to the expert.
Thanks, Andy. Okay, so you should be able to see my slide now. Yes, excellent. Okay. Hi, everybody. So yeah, as Andy said, I'm going to give more of an in-depth look into some of the electronics raw materials that I've been looking at over the past couple of years while I've been at ZEISS. This mostly fits into 2 separate groups of materials, the first being insulation materials and the second being semiconductor raw materials, as Andy touched on. So some of the different things that we want to look at when we're characterizing these samples, there's actually quite a lot of overlap between both of them in terms of what we're looking for a lot of the time. So we might be looking at connectivity and conductivity. So we might, for that, want to do things like particle analysis. We might want to do compositional or chemical analysis, look at voids, look at grains, layer coatings, film analyses. We might want to look at things like the identification of defects, scratches and cracks on the surface and internally within samples, and then also things like contamination and foreign objects. So the characterization of these raw materials is obviously really important because we want to make sure that the raw materials going into these electronic devices actually will work. And that is summed up quite nicely at the bottom of this slide. So characterization offers an opportunity to refine production and development parameters, and to fine-tune material properties, and then to develop new and advanced materials. So that's why we want to characterize them. I've summarized in this table some of the challenges, though, that we have with imaging and analyzing some of these materials. So not just electronic raw materials, but some other raw materials. These are some of the issues and some of the things that Andy touched on as well. So I'm not going to go through this entire table, but just pick out a few that I'm going to run through in this talk. Beam sensitivity, which can be linked with chemistry, can be an issue. So, for instance, low-density non-conductive materials, those are potentially are polymer-based. If we want to be able to resolve those specific features of interest, then it could be that we're not reaching the required resolution. We might not also be using the appropriate tool to be imaging our samples or performing the analysis. So how do we make sure that that's correct? Or then from that, how can we combine different tools to tell a full story about our samples? We might also have an issue with things like creating flat cross sections to be able to image our sample via other means. So how do we get around that problem? And then finally, again, stuff that Andy touched on, which is how do we generate quantifiable data from our images using a various different analytical image analysis options. So those are some of the challenges that I hope some of you watching identify with. And I'm just going to go through some examples of some of these different samples and how we're able to find solutions to those challenges. So just to summarize then with this introduction, I'm going to focus on three different aspects of how we're able to image and analyze these samples. That includes 2D imaging and analysis from things like scanning electron microscopy and light microscopy. I'm also going to talk about 3D imaging and analysis, so how we are able to use X-rays to image our sample non-destructively and completely in 3D. And then finally, how we can use some software-based tools. So not only to make our data and enhance our data as much as we can when it comes off the microscope, but also how we're able to then perform that digital image segmentation, quantification, and reporting. Onto the first group of electronic materials then, and that includes insulation materials. So I've got a handful of the different types of insulation electronic materials that are available on this slide. These, as you can see, range in morphology and structure. So some of them are layer-based, some of them are film or foil-based, some of them are particle-based, and some of them are fiber-based. So there's lots of different elements in there that we might want to image and characterize. There's differences in composition as well. So some of them might be more metallic-based, such as the copper adhesive tapes, which means that they're conductive, so easier to image. And then we have some other materials which are more polymer-based, such as the polyimide film, which are non-conductive, therefore, in theory, more difficult to image. These are all used for different applications as well. So these can be used for EMI or electromagnetic interference shielding or sealing, thermal conductivity, insulation, and things like heat transfer as well. So while this isn't an exhaustive list of all of the different insulation materials that we can be looking at, I'm going to show you some examples from some of these that are shown here. So first of all, then, I thought I would start off with, forgive me for saying, but a relatively straightforward example to image. And this is of a copper adhesive tape. So in this instance, we're looking at surface defects and contamination. And hopefully, clearly from this FE-SEM image, you can see some surface defects and some contamination. So the reason that I say that it's relatively easy to image is because it's obviously a metallic material. It's conductive inside something like an FE-SEM. And that means that it images well. We can image it at high vacuum, so we can increase the kV and maximize the potential of what we can get from something like a field emission SEM. So these are the images that we get from imaging it at 15 kV, but we can obviously do some other things. So once we're imaging in high vacuum mode and at a relatively high kV, we can get some chemical information. So this is traditionally from SEM EDS. We can check for inconsistencies in the chemistry of the copper foil itself, but we can also look at the chemistry of these contaminants and these surface features to try and understand where those contaminants are maybe coming from. We can also do things like EBSD, which is electron backscattered diffraction, which allows us to look at the crystallography of a variety of different samples. So in this case, we can look at the crystallography to understand how conductive it is and how well it works as a conductive medium. So as I mentioned, that's a relatively straightforward example, being able to image a conductive metallic sample at high kV and at high vacuum in an FE-SEM. But what about a sample where we have a mixture of materials? So this is an example of a thermal gap filler. This is where we have a series of metallic flakes in the sample. These are aluminium flakes. And then these are contained within a fluorosilicon polymer. So how do we image these mixed conductive and non-conductive materials? One of the ways that we can do that in FE-SEMs is by using what's called variable pressure mode, which is obtained at low vacuum. This is one of the options, which results, as you can see here, in us getting relatively decent SEM EDS chemical images. So this just shows that even at low vacuum mode and variable pressure, we can still get SEM EDS results from our sample in these challenging mixed material, conductive and non-conductive insulating materials. Taking it a step further then and getting even more challenging, this is an example of an incredibly beam sensitive material. So this is the polyimide film. We want to ideally be able to image this at high vacuum because this allows us to get much better imaging because we don't have the interaction of the electron being with air as we would have in low vacuum mode. So we want to make the most of the properties of the FE-SEM to image at high vacuum mode. One of the ways we can overcome this is by imaging in what we call sweet spot imaging mode. So this is where we can alter things like the kV or the accelerating voltage. We can change things like the detector system, and we can change things like the working distance that we're imaging at. So these images all show various imaging of polyimide film surfaces at 1 kV. As you see, the magnification goes up as we go from left to right. The low resolution image on the left shows the surface, quite a nondescript surface, which shows a series of scratches on the surface, which potentially means that this particular example isn't good enough to be used in an assortment of insulating applications. When we start to zoom in and really interrogate that surface at higher magnification, we notice a series of different flake-like features. So this just shows that at various different magnifications, we're able to get images of polyimide film even at high vacuum and at 1 kV using our FE-SEMs. Just want to show you this example quickly. So this is a relatively high resolution image of the same area comparing SE detector or the secondary electron detector in the FE-SEM and the in-lens detector. So what you see here is a comparison of the different features that the different detectors can bring out from our images. So the best thing about the in-lens detector is that it's located inside the Gemini column, which means that you get better illumination over the whole field of view of the image that you're collecting, which you can hopefully see in the in-lens detector image. There's no shadowing. It's pretty much in its entirety illuminated even at high resolution imaging. The in-lens detector is also perfectly set up for high resolution imaging in an FE-SEM, and it has really good surface sensitivity, which is really great for non-conductive materials such as these polyimide films. It also results in things like better contrast between different features, especially at low kV. So this example hopefully shows you that we are able, using our FE-SEMs and things like the in-lens detector, to be able to get decent images of really beam sensitive materials such as polyimide film at low kV and using a series of different detectors in the sweet spot imaging setup. So that's a bit of 2D imaging of insulation materials, and I think I'll touch on that again in a few slides' time. But for now, I just want to move on to talking a little bit about 3D imaging and how we can use X-ray microscopy to image and analyze our samples completely in 3D. So this is an example of the traditional workflow that we would use to image and analyze our 3D volumes. So usually we scan our sample at relatively low resolution, what we call a full field of view or an FSOV scan. We can then choose specific regions of interest to target at higher resolution using multi-scale tomography. So here I've got a multi-scale series of 3D scans from the thermal gap filler that I showed you a few slides ago. And this just shows how we can collect lower resolution, larger field of view tomographies, and then choose areas that we want to examine at higher resolution. So the reason we are able to do that on our X-ray microscopes is because we have a series of different objective lenses in the beam path. We also have and can have mounted on these microscopes what we call a flat panel. So this is what's traditionally found on traditional X-ray CT systems, but it allows us to get large field of views of larger samples at high resolution, which I'll come back to later on in the talk. But essentially, these objectives allow us to collect data sets using the 0.4x, the 4x, the 20x, and the relatively newly updated 40xP or 40x' objective. And just to compare, so the thermal gap filler images comparing data collected on the 4x and the 40x', here you should be able to see that, yeah, it's self-explanatory, really. We get way more information from imaging at high resolution using the 40xP, which shows the benefit using X-ray microscopy to do this multi-scale imaging in 3D, which is unique to our X-ray microscopes. Just to show that workflow then for the thermal gap filler, this is what it looks like, including some of the particle analysis. So we're able to collect multi-scale scans in 3D. We can do some AI-based reconstruction to improve the data and enhance it as much as we possibly can. We can then perform 3D particle segmentation. We can create things like multi-ROIs or multi-regions of interest to segment individual particles, instant segmentation, if you like, of what Andy talked about before. And then we can reconstruct that in 3D and perform full 3D particle analysis. So the chart I've shown here just shows an example for this gap filler of those particles and how we can measure things like sphericity of the different particles through the entire volume. So I now want to focus very briefly on the AI-based reconstruction and how that can help us improve the data so we can get the best segmentation and quantification results we possibly can at the end of this workflow. So the AI-based 3D reconstruction usually starts off with collecting data that you're not satisfied with. So this is an example of a filtered back projection reconstruction, often called FDK, which is usually the sort of bog standard, if you like, method that people use to reconstruct their 3D data sets. You can obviously see, hopefully, that it's quite noisy. Maybe we wouldn't be satisfied with this data set. We could probably get some segmentations of those particles out. But yeah, we'd ideally like the data to be a little bit better. So instead of reconstructing it using FDK, we can reconstruct it using our AI-based approach, which is called Deep Recon Pro. And as you should be able to see quite clearly here, we reduce the noise and we massively improve the contrast between the particles and the background. So this, again, allows for much nicer segmentations. Something I should point out here as well is that this is AI-based 3D reconstruction, but it's non-generative AI. So it isn't just making up data, it is actually working off of our data sets to essentially strip out the noise and improve the contrast. So we've got to this point. We can also perform some other reconstruction to eliminate some subtle artifacts that we sometimes have in samples that have been scanned at a relatively low kV. This yellow circle here, I'm not sure if you'll be able to see, but we've got these very, very subtle phase artifact lines around the outside of some of these particles, which this phase evolved reconstruction approach eliminates. So again, this leads us to get easier and better segmentations of our data sets, which leads to much more reliable quantification later on. So I've talked a little bit about particle analysis. I'm just going to touch on a few other things that we can get here. So this is the entire width of our thermal gap filler. As well as particle analysis, we can do things like surface roughness, surface thickness of our samples. So this could be an important measure that we might want when we're thinking about using these raw materials in our electronic devices. Sometimes roughness on a surface isn't all that helpful. So we can measure that in methods such as this from the 3D volumes. And from studying the 2D slices, we can see that it's actually those aluminium particles within the sample that are actually contributing to this sample roughness. So it could be a case where the manufacturer of this material goes back to the drawing board and thinks about the particle sizes that they're using to help eliminate that surface roughness. So that's thermal gap filler. I now briefly want to touch on another quite challenging sample to image, which is polyester films. So these are obviously very beam sensitive. You'd think they're actually quite homogeneous and quite boring to look at, but actually they've got quite a lot going on internally. So these polyester films are around about 75 microns thick, and we have used X-ray microscopy to image these in 3D. What we've actually noticed from high resolution multi-scale scans of this particular film is that we've got a series of high density particles found internally within the film itself. Now, it turns out that these particles, it's usually aluminium silicate particles, are used as additional insulation in these materials to try and enhance those insulation properties. And they're so small, they're less than 10 microns big usually, but we're able to pick them up and image them in from 3D microscopy. So I've got a short video here that I'm just going to play, which shows not only the surface features of this film, but also those internal particles. I might just actually stop talking through that video playing because I'm not sure my internet would cope, but we'll see how we go. So we can look at the surface of the film. We can look for scratches, defects. Obviously, because it's 3D microscopy, we can look inside. We can pick out those individual dense insulating particles. We can look at their distribution through the thickness of the film, and then we can perform particle analysis on them. So this is an example of where we're able to pick out these really teeny tiny particles through 3D X-ray imaging. And that's just summarized in this slide here. So we're able to high resolution scans, which are then able to segment the particles and then perform a particle analysis. So here, just to finish off the polyester film story, this is an example of a high resolution scan using the 40x prime objective that was collected at 380 nanometers voxel size. And here we're able to pick out those individual particles, but also the fact that they have air pockets or voids around them. So this 3D reconstruction here, they look like little flies almost, but these are in fact 3D reconstructions of those teeny tiny particles that are surrounded by air pockets. As I mentioned, we can do 3D particle distribution of these particles throughout the entire width and length of the film. And one of the things that's really important with the manufacture of these films is that we have a evenly dispersed distribution of these particles through the entirety of the film. So as I mentioned, they are there to enhance thermal insulation, but careful formulation is needed to avoid clumping and to provide even dispersal through the film. So again, we can use 3D imaging to measure that even distribution, which is shown by this histogram here. So that's insulation materials. I now want to move on to talking briefly about some semiconductor raw materials. So I'm sure most of you are familiar with some of the 3D imaging that's been used to look at PCBs, to look at chip packages, to look at things like solder fatigue cracks, and to look at bump voids and defects. But what I'm mostly interested in here is the materials that those boards and those chip packages are made out of. So I'm going to focus on copper clad laminates and perf boards, which is a type of strip board. So for those of you who aren't familiar with copper-clad laminates, essentially they're the building blocks and foundation for PCB manufacturing, as it says here on this slide. This is a very crude cross-section cartoon that I made yesterday. It's copper-clad laminates are essentially made up of 3 or 4 different components. You usually have a copper foil either on one surface or on both surfaces that acts as a conductive layer. You then have some sort of reinforcing material, which is usually in the form of glass fabric weaves. In this case, it's fiberglass. This is non-conductive. It's used for mechanical strength and for stability. And then finally, holding it all together, we have this resin filler, which is usually an epoxy with a series of insulating particles in it. And this is for insulation and heat resistance. So as you can see here, again, we've got a mixture of a conductive layer on either side and then non-conductive material inside. So how do we image that successfully? So first of all, I want to talk about the surface of the copper foil. This is really important because essentially when PCBs are manufactured, you have a series of etching that occurs on the surface of the copper layer, which means that this needs to be treated before it goes through that step. It needs to be polished, it needs to be flat. And quite clearly in this example here, we have an example that hasn't been through that or has been through it and hasn't been through it correctly, if you like. So we can see a series of scratches and dents and various other features on this surface. So here we're using sweet spot imaging, excuse me, to image this copper-clad laminate surface at different kVs. So we've got high kV, 20 kV, 10, and then 2 on the right-hand side. And obviously from each of these images, you can see some variation in what we can actually see. The 20 kV scan image actually shows not too much in the way of surface information, but the lower kV scan really picks out all of that surface defects and the dirt that you find located on the surface. We can see the same for this example as well. So these images were taken of this defect notch on the surface at a slightly longer working distance, but at the similar 20, 10, and 3 kV. So this again shows how choosing the correct imaging parameters brings out different aspects of the surface of samples, depending on what it is that we're interested in. We can also look at defects in cross-section. So this shows an example of a cross-section that was made doing conventional grinding and polishing. You can see that we have the copper layer on the top, and then beneath that we have all of those particles that are found within the epoxy resin. The yellow arrow in that first left-hand image indicates a notch that we have in the surface of the copper itself. Then we can go through various phases of performing SEN EDS, so we can get some chemical information, again, making sure that the copper is of a homogeneous chemistry. And then we can perform some 2D image analysis. So in this example, all we're interested in is segmenting that copper layer, and then we can look at thickness variations and roughness of the surface and how that varies through different samples that either have these defects or don't have these defects. So this just shows how we can do connected microscopy in a way. We can do conventional FE-SEM imaging, we can perform chemical imaging from SEN EDS, and then we can take that a step further and do some image segmentation. This slide just shows a variety of other features that we can see in the copper-clad laminate. So yeah, here you see a full width and you see that weave, the different weaves of the fiberglass running through the center part of the sample. You can see various different magnifications of the cross sections through some of those fiberglass fibers. And then we have some really nice views at the bottom of this copper layer and how that interacts with that interior non-conductive layer. We can also look for things in the resin material. So this is an example which shows the poor mixing of the resin with those insulation particles. You can see these black areas which don't contain any of these particles, which shows poor mixing of the resin, which could inevitably have an influence on how well this copper-clad laminate works when it's put into a PCB. Again, we can do things like SEN EDS. So this allows us to check the chemistry of different aspects of the laminate. We can look at the glass fiber chemistry, the resin matrix particles chemistry, and the resin matrix itself. Look at the recyclability, and then ultimately quantify the different chemistries and components that are in here based on the SCN EDS. We can also do image analysis of some of the different components. So as I mentioned, there are three main components in here. We have the copper layer, we have the particles within the resin, and then we have the fiberglass fibers, which run through the whole of the weave in the center part of the sample. So this is an example of this AI-assisted image segmentation called arivis Clad that Andy mentioned previously. This is set up with Meta's Segment Anything model, or the SAM model, which allows for really easy annotations of the different features within a variety of different sample types. So in this workflow, I've created a few very simple annotations in the top left-hand image. I've painted the copper layer. I've annotated in purple some of the particles in the resin, and then the yellow shows a few of the cross-sections of the fiberglass that I've labeled myself. This took about 4 or 5 minutes to do. We can then train a model based on those annotations, and then some segmentation predictions are made, as you see in the middle image. So even based off of those very few annotations, we're able to get some really good models and really good predictions of the segmentation. And then, of course, once we're happy with it, we can let that model run, and then we can segment it for our whole data set. And that's not all. As Andy mentioned, we're able to do instance-based segmentation. So we can segment the copper foil, we can segment the individual particles within the resin, and then we can segment the individual cross-sections of the different fibers in the fiberglass. So this allows us to check for inconsistencies in particle size, particle shape, and also allows us to potentially lead to defect analysis in these copper-clad laminates. So once we have these models, we can also take it a step further, where we can import those models into another software option, which allows us to then get the full particle analysis measurements. So we can look at a whole heap of different things, ranging from volume, shape, size, sphericity, elongation, max Fourier diameter, whatever it is we're interested in. Those can then be measured. And then that enables us to do some really efficient reporting. So we can make tables, we can make charts and graphs, and then that can all be put together in 𝗠cie𝗿𝗄𝘀 as easily extractable report. One other thing I just wanted to touch on very quickly is that the 2D image analysis doesn't have to be done just for FE-cen images. We can do it for any image, really. Here is an example of a cross-section through the copper-clad laminate taken on a light microscope, where we're able to do it to create some very simple annotations. We can create from that some very simple segmentations, and then a composite image at the end, which then allows us to do some further segmentations. So in terms of the copper-clad laminate then, I just want to finish that off by talking about some 3D imaging. We can use X-ray microscopy to do this. Again, this is an example where our AI-assisted reconstruction using Deep Recon Pro can help improve the data. So hopefully on the left-hand side, you can see a traditionally reconstructed FDK dataset, which obviously we can't hardly see anything in. And once we've run it through the AI process, we start to pull out all of that really relevant information, strip out the noise, and then we can perform 3D analysis. So again, I've got another video on the next slide, which shows the 3D segmentation of some of these glass fiber bundles. So again, we can use this to check for defects. We can use it to check the consistency of the bundles. We can use it to check for the consistency of the diameter and the length of these different fiberglass bundles. So it's a really useful tool in combination with the other methods for figuring out stuff about our samples. Just want to touch quickly on electronic perf boards. So this is an entire perf board of about 5 by 8 or 9 centimeters, which was scanned using the flat panel on the X-ray microscope that I mentioned previously. This was at relatively high resolution of about 15 microns voxel size. And again, we can do analysis of different components within this. So we can look at the thickness variations of those copper pads that you see scattered across the surface to make sure that they're consistent. And then when they come off the production line, they're of a similar shape and size. And the same for the holes as well. So we can ensure that the hole diameter and shape and size is consistent for every part of this perf board. We can also look for things like cracks, which are highlighted by this yellow arrow. So again, it's an opportunity to look for defects in 3D. And again, as I mentioned, we can do some 2D imaging at low KB of these non-conductive materials, and then we can perform some image analysis. So here we segmented the copper pads as we did with the copper clad laminate. So I very now want to briefly talk, because I am very aware I'm running out of time, but I want to talk very quickly about the elastomer gasket case studies and how we have applied 2 separate workflows to those. Characterization of these materials is important to make sure that the particles are actually conductive and they're doing their job properly. The first workflow is a 3D imaging workflow, and the second workflow is more of a preparation workflow where we can cut large cross sections using the laser fib to then perform 2D imaging and analysis and subsequent quantification. So this is what the scans of a gasket look like. We have a series of metallic particles that are copper in composition, but then are surrounded by a series of silver coatings, and those are in a fluorosilicon polymer matrix. So it's important that these particles are studied to allow us to understand things like connectivity and conductivity. So again, here we've applied similar approaches to the previous examples where we've used Deep Recon Pro to enhance the data. We've then performed segmentation on things like the coatings to ensure that they're consistent. And we've done things like aspect ratio particle analysis to make sure that the particles are of the correct shape and size. Talking about the particle segmentation, we can do analyses such as the difference between the connected versus the unconnected particles, again, which means that we are ensuring that we're forming these pathways within these insulating materials. We found in this example that 99.38% of the particles are actually connected, which allows for good connectivity and conductivity. We can also combine that with some other particle analysis. So this chart on the right-hand side just shows the length of the different particle connections that we have in this sample. So we find that we have up to 232 individual particles that are connected, forming that conductivity connection through the sample. So it's not just about the segmentations. This can actually give us some usable connectivity data. We can also do things like segmenting individual particles. So this is an example where we have the pores, the copper and the outer silver coating segmented on the versa. But we can also take that one step further and do some nanotomographic imaging on our Ultra XRM system. So this particular example is at 64 nanometers voxel size. So it's essentially bringing synchrotron level resolution to a laboratory-based system. We notice with this example that individual pores are found within the particle rather than one giant pore as we were seeing in the previous example. So this shows how imaging at the correct resolution and a really high resolution at that allows us to pick out more information from our samples. The second workflow then starts with using a laser fib to create a flat surface. So we have issues with imaging and analyzing the surface as it comes off the production line because it's not smooth and it's challenging because it has a relief. We can use something called a laser fib, which is a laser attached to a 𝗶𝗳𝗀 to create these really large cross sections in very little time at all. So the width of this particular example is 1.6 millimeters, and we're able to blast through that in around about a minute. So that allows for this very, very quick cross-sectioning, which otherwise 𝗶𝗳𝗀 would be very difficult to do. It allows us to get a smooth surface for further imaging and analysis. We can it also works very well on heterogeneous samples. So these mixed materials where we have hard and soft materials, it allows us to cut through those very, very easily. So this is a great example of laser fib working on unusual samples, let's say. Again, we can do things like SEM EDS, so we can look at the thickness of those silver coatings around the outside of the particles and understand the best detector to use for these imaging parameters. So backscattered mode gives us the best imaging and contrast for this particular sample. We can also perform sweet spot imaging to look at these strange defects where that silver layer has actually penetrated into the center part of the particle. We notice in this particular example that actually having a longer working distance at 8.5 millimeters works best for observing these features. So again, another example of when sweet spot imaging and choosing the correct imaging parameters in your FESEM is necessary to be able to see different things in your sample. Again, then, as I have shown you with a few of the other examples, we can take those FESEM images, we can annotate them, and then we can perform AI-based segmentation using our AI-based tools. And that's really great on samples like this, where we've also got 3D data, because we can use the 2D grain segmentations to complement the 3D data analyses to paint a more complete story about what's going on in our samples. So, and that's what I wanted to say. I'm just bringing up this this table just to show you how hopefully those challenges I mentioned at the beginning, hopefully I have shown you a few of the different solutions in both 2D and 3D and some of our image analysis tools that can overcome some of those challenges. Just to summarize that then, for 2D imaging and analysis, we can use FESEM, light microscopy, and laser FIBs. For 3D imaging, we can use microscopes such as the Context, the Versa, and the Ultra to perform high-resolution 3D imaging. We can use AI-assisted Deep Recon Pro and 𝗶hes_evolve to really enhance the data and to improve it to a point that we get way more information from it. And then finally, we can perform image-based segmentation and analysis using tools such as arivis Cloud, arivis Pro, Intelisys, and Zen Core EM. Thank you very much.
Awesome job, Eden. A lot of that is new for me as well. So amazing stuff. A lot coming at us. Thank you, everyone, for attending again. Thank you so much again for attending today.